Just as my introduction, I am an MSc Cytopathology and Histopathology, and we proceed. The objectives of this training today, one is to advance knowledge and skills in laboratory data analysis, to inform policy and research insights, to understand key components of laboratory data analysis, also to empower laboratory personnel to actively engage in lab data analysis for operational research, and also any other healthcare worker who has joined today's webinar. This cuts across any healthcare personnel to actively engage in data analysis for operational research. So we also have an objective that we intend to accomplish, and that is to review key types and application of statistical techniques in lab analysis of actual laboratory data, or data that we collect within the healthcare space. So basically, statistics is a branch of mathematics, but deals with collection, organization, and analysis, interpretation, and presentation of data. So data must be collected first. So you must have tools to collect data. For example, our laboratory workbooks, our laboratory records, our patient forms, those tools that we use to collect data from our patients. And one of the example of a tool is the laboratory request form, is a data collection tool, because we need to know the age of this patient, the gender, and so forth. Now we need to organize this data. And the organization of data is, once you've collected, you want to put this data in an organized way, so that somebody can have, when they have a glimpse of it, they are able to understand the data. It's not put in a state that is way haphazard. So data has to be organized. Then after organization, we need to analyze this data. And that's why we will be building our entire training today. Analysis of data is key, because once you analyze the data, then this data can be interpreted. And therefore, once you are able to interpret the data, now you can present it, for example, in bar graph, in charts, and so forth. Biostatistics is all applications of statistics to biology, and that is life. The application of statistical principles in medicine, public health, or biology is actually biostatistics. So a research basically is good to remember that research is a scientific study of a phenomenon of interest, or is a scientific inquiry into a problem. So we have the population, which is actually the set of individuals, every person. So for example, we want to do some survey about customer satisfaction within our laboratory. So we cannot be able to take the entire population that is served by that lab. So we might have come up with what we call a sample. So from that population, now we have a sample. So actually, the entire collection of a set of individuals is a population. But data analysis, we all usually do it among, or rather out of a sample. And a sample should be a subset of a population. That is a representative subset of that population. So parameter is actually the numerical characteristic of that population. And a variable, it is a characteristic that can take on different values. For example, age. Age can be a variable, and so every different person can have different age. Some can have the same age, but we are saying that it's a characteristic that can take on different values. It's possible that age can be 20, can be 30, can be 19. Those are different values. Weight can be different, and so forth. So we have qualitative, which is an attribute variable, and we have a quantitative variable. So from the word qualitative, this one is a characteristic that picks on a non-numeric. So is actually reported as a non-numeric. For example, color. Let's talk of race, talk of gender, talk of type of disease. Is it malaria? Is it cancer? That's a qualitative. It's an attribute variable. So it's non-numeric. But a quantitative variable is one that can be reported numerically. For example, age, height, and so forth. Now, for you to be able to analyze any data, you must classify this data. But before that, there are types of statistics that is just good for us to know about. We have kinds of statistics, or other types, and one is theoretical statistics, which is mathematical statistics. We have applied statistics, which we will measure on. And in applied statistics, that's when now we apply inferencing. We apply what we call inferential statistics, where we draw conclusion about a population. That's inferencing. So inference is just drawing a conclusion. Now you can do some research, for example, in that survey. Then you want to draw a conclusion out of the survey. You need to do what we call inferential statistics. But before you do the inferential statistics, there is another arm of the statistics, applied statistics, which is descriptive. you will give the description. For example, you go into a field and you want to do some, maybe let's take an example of a certain test. For example, let's do of LFTs, liver function test. Within that incidence, or rather within that cohort, you will get male and female. You will get different age groups. So you'll come with what we call descriptive statistics out of it, which is organizing, summarizing, and presenting data. You organize and summarize. That gives a summary. For example, majority of the consented, or rather majority of the participants who are above age 60 years of, or 60 years of age. That means you're giving a description. There is nothing, you're not drawing a conclusion. Now you're talking about the mean age was this, so you're describing that particular. So that becomes under it comes under descriptive statistics. Now, when you are writing a paper, you will not do inferential statistics first. You will first of all do what you call descriptive statistics. Even under discussion, you will give a description. And you see most papers have written it, they put it as this laboratory characteristics. Laboratory characteristics, they are putting it as descriptive statistics now. And now they'll give the age, the gender, how the gender was distributed among participants, the age distribution within the participants. So they're giving a descriptive way of it. For example, you're doing research in diabetes. For example, you do about the age, the gender, and then you come about to do about the mean, maybe HbA1c measurement, or you come up with an SD and so forth, which we'll just handle in a few. Now, types of data, before we dive further, we need to get to understand that different types of data. And in these different types of data, it's important to know that, one, we have categorical or qualitative data. Just as we said, the variable, types of variables. So this is data that we are collecting. So it is either categorical or qualitative data, or we can have numerical or quantitative data. So some will call it numerical data or quantitative data. And within this, we can have what we call the normal data, which comes from the word nominal. Then you have the ordinal data. Then you have the discrete data. And then you have the continuous data under the numerical. So categorical, we can either have normal data or ordinal data. And I'll be defining this. For example, in normal data, you're getting, for example, let's talk of female, male. That is categorical because it's qualitative, it's not quantitative. It cannot be measured, or rather put in a numerical, reported numerically. But it's a normal data in such that it's a name. It's coming from a name, whereby you are either female or a male. But now when you say of ordinal data, this is coming from the word order. So this data can be ordered. For example, you're talking about satisfaction index, 1 as lowest satisfaction and 5 as highest. You see, there's an order there. And so when somebody is highly satisfied, it means they are more satisfied. When somebody is averagely satisfied, it means they are less satisfied compared to the highly satisfied. So that becomes ordinal data. Yeah, under numerical or quantitative data, we have discrete data and continuous data. Now, in discrete data, you're talking about it's characterized by gaps, or what you call interruptions. What do I mean by interruptions? Is that in this kind of data, we cannot have decimal points. We only have what you call whole numbers. So those are interruptions. They cannot assume anything within that range. They have some gaps. For example, number of live births. You cannot say we have 2.5 live births. No, we will say we have either 2 out of 1,000 live births, 100 out of 1,000 live births. You see, we do not have a decimal point coming in here. Number of children, for example. When you talk of continuous variable, or rather continuous data, this one, it continues. It is from the word continuous. So it does not possess the gaps or interruptions. So it can take any range of value within it. And that can be like height. So data, height data is a continuous, because it can be 1.23 meters. You can be 1 meter. You can be 5 meters. So it has no gaps or interruptions. And that's another type of data. Now, we tackle the types of variables, and it's good to mention as we proceed that a variable is actually a characteristic that can take on different values. And this includes, for example, height, weight, age, race, attitude, and different variables that we know about. So these words are used interchangeably between the types of data and types of variables. Now, for example, under the quantitative variable, I said we can have discrete variable or a continuous. The previous one was data, but here we are classifying it as discrete variable or continuous variable, which is the same thing. For example, age is a quantitative variable because it can be reported numerically. Number of beds in a hospital, height or weight. But out of that quantitative variable, we can have either discrete or is continuous variable. And a discrete variable is just simply, it takes whole numbers only, nothing else. So it possesses gaps. While continuous variable is one that can take anything about it. So there are no interruptions. It can take also decimal points, can include also decimal points. They are allowed. So we gave examples from the data that are types of data when we were dealing with the types of data before. So under qualitative variable, this one is a non-numeric one. So in this non-numeric characteristic, you just giving, for example, gender or color. You cannot report it numerically. And of course, it's important to mention that there are other types of variables which you can classify them as dependent variable, which is influenced by an independent variable. So it is the outcome. So when you're doing your research, you must know and understand which one is your dependent variable, which one is influenced, and which one is independent variable. It is not influenced. For example, you want to study about the relationship between height, weight, and BMI. So, you come up and understand that you need to define which is your outcome, which we call dependent variable. For example, becomes the BMI, because BMI will be influenced by your age, by your height and weight. And so height and weight becomes your independent variable because it does not depend on BMI. But BMI on the inverse depends on it. So that becomes your your dependent variable BMI, and your independent variable is the height and weight. So it's not affected by the outcome. Then there is confounding variable. For example, you're doing a research in diabetes. We know that in diabetes we have children who are diabetic, adolescents, kids, pediatrics, but we have also quite number who are elderly who have diabetes. And so you are studying something within that, and now a confounding variable within that becomes age. Age becomes a confounding variable because it is highly expected that with age people develop diabetes. So a confounding variable is one that has potential relationship or association with the cause of the problem. Maybe you're not interested in age, you're doing something else, but out of it you come up and say that age is a confounding variable, and that's how now you need to match or do something we call matching in research to ensure that this confounding variable is taken care of and does not influence your outcome. Now, look at this, an example of independent, dependent, and confounding variable. You look at parity as an independent variable, but parity is affecting the weight of babies. So we are looking at low birth weight here as a dependent variable. So, for example, talk of women who have a higher parity, who have higher number of children had maybe in your research you are giving an assumption that they might give birth to low birth weight babies, and so you are insinuating that parity remains your independent variable while low birth weight is dependent variable. But now again, the age of a mother can also influence the birth weight, and you are not interested about the age, and now that becomes your confounding variable. So while analyzing data, this is key, that you need to understand that this might be a confounding variable for me. It has potential association with low birth weight as much as I'm looking at parity as my independent variable. Now, in any status you want to do data analysis, once you know about your variable, you classify correctly your variable, you now come up with the type of data you're collecting. You know which type of data you have. You understand now, you understand the descriptive part and the inferential, which will come later. Now you need to now come up with what you call measurement scale. Now, when you talk of measurement scale, measurement is actually assignment of numbers to objects or events according to a set of rules. In statistics, when you're doing measurement, it's actually you are assigning numbers to objects or events according to a set rules. So within these, you must have what you call measurement scale. And there are 4 levels of measurement of data before you do any data analysis. And this includes when data is qualitative or categorical, or your data is quantitative or numerical. For example, you're saying that social status, and you're saying low, medium, and high income level, for example. That will be ordinal, which is categorical. They are categories, they are not numerical. And maybe you want to talk of salary, and that becomes quantitative. Now, that is numerical. Now, in you'll have different types of this sort of data, and now you need to have the specific measurement scale. We'll have what we call the nominal scale, ordinal scale, interval, in ratio scale. Now, once you understand the nominal scale, it is limited to particular analysis. That's when now you can analyze your data. For example, nominal comes from the word naming. So when you talk of nominal scale, we are looking at those particular data that will require measurement of scale that only allows naming. Blue, for example, color, blue, red, green. For example, gender, female, male. For example, talk of disease type, cancer, malaria. Those are nominal. Now, you can only do what you call mode here. You can only calculate mode, which you'll be handling. You cannot do anything else. We'll be handling in a very short while. You cannot do anything else on this data. You cannot do mean on female and male. You cannot say we have a mean of female or male gender. No, gender you cannot do any. Marital status, you cannot do anything like mean, median. No, you'll only do mode. That means which was the most appearing group. For example, you do and females are 60% and 40% are males, then that means the most appearing ones were males. So you can only analyze descriptive statistics where you can give there is only the mode. Now, when it's ordinal, ordinal is a naming actually, but in a certain order. So it's a category that has a ranked order. So it's arranged in a certain order. For example, let's talk about satisfaction index, and you say very satisfied, satisfied, dissatisfied, or very dissatisfied. You see, that's an order. So in such a way, this kind of data, you will call it ordinal. And so this kind of data will require a measurement scale called ordinal scale. And what you can do on this data, you can describe the median and the mode. You cannot have the mean. But best measure of spread here is IQR, which is interquartile range. So if you want to do what we call spread, measuring spread of it, or which we'll be handling shortly, apart from central tendency, we are talking about variation or spread of data. So you'll use what you call the interquartile range. But remember, in nominal, there's no measure of spread. You cannot look at measure of spread. And look here, in ordinal, you cannot do mean. You can only give the median, which was the median, and what was the mode. That one can be given, and what was the IQR, the interquartile range. Then we have another data under the quantitative or numerical one, and this one is interval scale. So in interval scale, 0 is arbitrary, and in 0 is arbitrary. Then this means that the 0 point on a scale does not signify a true 0. It means this, that 0, it doesn't mean that there is nothing. In interval scale, 0 means something. It doesn't mean that absolutely there is nothing. Yeah, absolute absence. No. So in interval scale, for example, which is commonest, is a temperature. When you say 0 degrees Celsius, it doesn't mean we completely have no heat. It only means that the heat is at the level of 0 degrees. So 0 does not mean that it's absence of the quantity being measured. And this is the second highest level of measurement. So the lowest measurement scale is nominal. Then the highest measurement scale is ratio. And ratio says 0 is not arbitrary, means that 0 point on a scale signifies a true or absolute absence of something. For example, when you want to find out how much money you have. So when you say I have 0 money, it means you completely have nothing. And that is opposite to what we call the interval scale. Now, what can you do on interval scale? One is you can do mean, you can do median, you can do mode, you can do range when it is spread, you can do variance, you can do standard deviation, and you can give what you call the interquartile range. But when it is ratio, now you can also do mean, you can do median, you can do mode. Now you can do also range, you can do variance, you can do SD, and you can do IQR, which is interquartile range. So this one allows all central tendency to be provided, and also measures of spread can be provided in this kind of data. So once you get your data, you need to define which measurement of scale. For example, you are doing a research among the diabetes, and I'll say first variable is, for example, gender. Now that becomes nominal. Now you can only give the mode and describe the mode. The most appearing participants were males. Now, ordinal scale, you will now, for example, talk of maybe satisfaction of service within that particular laboratory, and now you'll give the order. And now you'll give the median, the mode, and the IQR for that matter. When it comes to the interval scale, now you look, do you have anything like you're taking, for example, temperature from those particular participants. You're measuring maybe their temperatures. If it is ratio, you're looking at the completeness of it, and that means you can look at maybe, for example, talk of HbA1c measurement, RBS, because in RBS, if you say it is 0, it means there is no complete sugar. So that means you take all those, and now it will be under ratio scale. Now, these are just examples. Nominal data is like, for example, the marital status, sex, gender, ethnicity. Ordinal, like student letter grade, NFL team rankings, and so forth. For example, you say this is the first, second, third, maybe in athletics. So, you know, this is a certain order. So first runners up, second runners up, and so forth. The champion, yeah. So interval scale is, for example, the temperature, and the SAT scores, which is the IQ. And for example, year. For example, you want to get some data like which year were you, maybe which is your birth year. So somebody says 2026, another one says 1993. You see? So when somebody says that, they cannot give a year like 0. So that's an interval scale. So in interval scale, 2023 to 2033 and 2033 to 2040 has the same interval. So 0 here does not mean absolute absence of something. Then the ratio is like age, height, and weight. Now, descriptive statistics. Now you've gotten your data and you want to describe your data. The measures of central tendency that gives descriptive statistics of your data includes the mean, the median, and the mode. And I'll not handle this much because it's common. So you need to give the mean age of your data, the median age of your data, and probably the mode age of your data. I'm giving age as a variable, for example. So you describe that. So when you proceed to the next level, you can prescribe the range. For example, if the highest participant was 102 years and the youngest participant was 2 years, you give the range. You take 102 minus 2, that's 100. Then you come up with what you call the interquartile range. And this is found by dividing data into 4 equal parts. So you come up with what you call the Q1, Q2, Q3. Q2 is actually the median, because Q1 is the first quarter of your data. Then the second quarter of your data now makes it 50%, and that is Q2. And now Q3 is the what you call the 3/4 of part of your data. So to get the interquartile range, you'll take the Q3 minus Q2, I mean Q1, and you get now what is the interquartile range. And that shows the spread. Now, when you talk of descriptive statistics, we will talk of either measures of central tendency, which measures the center of data, or you'll talk of measures of dispersion, or both. And measures of dispersion is talking about how spread, how variation is the data. Now we talk about the variance, for example. We'll talk about the standard deviation and maybe coefficient of variation. Just the variance, to just mention about it, is about now the individual measurement, how they vary from the what you call the mean. So variance is actually the individual measurement. For example, you take the age of the participants that you have, and now you get the mean age of the entire sample size. Now you will get each individual age difference from the mean. and now you square that, and you divide by the number of total number of participants, and now you get the variance. So that's how you get the variance. Now you get how each individual has varied from the mean. Now, when you talk of coefficient of variation now, you will now find your standard deviation. Standard deviation is actually the square root of the variance. Now, when you get the standard deviation, once you've calculated the variance, you've done the square root, you get it, you will put it over mean. So we call it measure of variability. So coefficient of variation is measure of variability, and you multiply by 100. This one is done to compare, for example, two groups, and you want to see which group has highest variability. So definitely, if you get 11% variability and one has 15%, then you'll say age difference in group one, for example, female and male, you're doing a mean age for female, mean age for males. Now you want to see the variability. Now you have to do coefficient of variation by standard deviation over mean, and now you get the variability, and which one is varying, is highly having a higher variation. Yeah. So while you've done that and done the descriptive part of your work, there are types of distributions you need to know, and these I'll just mention. There is what you call the normal distribution. It's bell-shaped. If your data looks like this first graph, it's bell-shaped. It's like tumbo, just like the stomach. We call it normal distribution. And in this kind of data now, you can describe the mean and the SD, standard deviation, and the mean is used here because in this kind of data, the mean equals the median and the median equals the mode. So it is equal. The mean is the same as the median and the mode. Now, in such kind of data, your work will be to describe only mean and SD because the mode and the median, we always say in measure of central tendency, mean is less stable compared to the median and compared to the mode. You see, now in this case, right skew, in this second one, you can see the data is moving, is being pulled on the right, so it's called right skew. And in such kind of data, you cannot use mean because the mean will be affected by the outlier, the highest, or the extreme value here, the lowest. You see the lowest graph. So this mean will be pulled and be affected. So you cannot use the mean to describe your data here. Now here you'll use the median and the IQR inter-quartile range to describe your data. So in such kind of data, you don't write about the mean. You write about the median and IQR because the median here is more stable than the mean. The mean will not give a good description because, for example, you have been taking data of age and one person is 5 years, other people are within 5 years up to 30 years. Then one of the persons comes with, for example, talk of 100 years. So you see, most people are lying between 5 and 20, but somebody here has come extremely the other side. So they will pull the mean. They will pull the mean of this particular data. And so the median will be the best to give a description when you are writing on such a kind of data. Similarly to such a data that is pulled on the left, that is what happens. You use now the median and the interquartile range to give a description of that kind of data. We are coming to a very nice part here. And maybe you've been reading papers, those who read publications, and you will see inferences. You will see some words used as confidence interval, p-value, hypothesis. So this is key. Under inferential statistics, actually, the word infra comes from the word generalization or making what you call a conclusion. Yeah. So you've taken everything. Now you want to conclude. For example, such kind of study, you talk of maybe cervical cancer among diabetes mellitus patients, you know. So definitely here, cervical cancer is found in female. So the gender here will be female. And there's no need for you to take gender and say 100% were female because, of course, that is common sense. And so you cannot use gender as a variable in that particular research. But here you're looking at what are the cervical cancers that we find in the diabetes mellitus patients. So you look at this, you will now need to make a conclusion about it, a generalized conclusion. So that's what we call inferential statistics. You want to relate, is diabetes related with cervical cancer? So you want to make a conclusion out of it. So you'll need what we call inferential statistics. Remember, we talked about descriptive statistics and inferential statistics. Now, in these inferential statistics, is actually a procedure by which we reach a conclusion, yeah, about a population on the basis of the information that we found in a sample. So there are two types, and there is one we call the confidence interval, which is an estimation, and there is one we call the hypothesis, which is a conclusion, which is a prediction, yeah. So when we talk of hypothesis, is actually when a researcher, you want to give a valid assumption about a certain unknown parameter. So for example, this is a hypothesis, is actually an assumption. So for example, you're saying there is no association between HbA1c and cervical abnormalities in DM patients or in diabetes mellitus patients. So you're saying this is what we call null hypothesis, the hypothesis of no association, no difference. So this null hypothesis, you as a researcher, you're saying there is no association between customer satisfaction index and maybe a second visit, yeah, a second visit. So you want to look, is there association between satisfaction of the clients we are serving with a probable second visit? So of course that means you'll have data collected on how are you satisfied with our service. You have data to be collected, which visit, which number of visits have you made in this place. And for example, you get maybe those who are coming for the third visit, they're saying we are highly satisfied, and those who are coming for the first visit, they are saying maybe we're not satisfied, or vice versa. So is there association between the number, number of visits to our laboratory versus the satisfaction index, for example? Now we have another type of hypothesis, which there is association between HbA1c and cervical abnormalities in DM patient. Now this one is called the alternative hypothesis. Yeah. So anything that says no association, no difference, there is, or equal. Some will use the word there is equality. Okay, the mean age of females and male patients that we attended to is equal. So meaning that of course you're talking about completely there is no association. Yeah. Now in null hypothesis, it's also sometimes referred as no difference, since it has a statement of agreement with no difference or no relationship, or equal. So you talk of it's equal. The mean age of female and the mean age of males in diabetes patient is equal. So you see, this you mean that you collect the number of you collect different age of the patients coming for diabetes mellitus clinic, and you analyze the mean age for female and the mean age for males, and you find it is equal. So that means that there's no difference, there's no relationship, yeah, of gender and the mean age of diabetes. Or maybe you find that the mean age of diabetes is higher among males and females. So that will mean something, that probably males will have a higher age. Males will they have an advanced age before they develop diabetes compared to females. Or maybe say that females now will get diabetes. They have a risk of getting diabetes at an early age. That is the point. Now when you talk of alternative hypothesis, we are saying that there is no difference. I mean, there is a difference, yeah. So, and this is when you do the mean age for diabetes females and maybe the mean age for diabetes male, and you find that there is a difference. So you say the gender does not relate or associate. There is no association between gender and the age of diabetes patient. So there's no relationship. Now, when you calculate that, we always have what we call the p-value. So once you get a p-value, for example, a p-value of 0.03, we say that there is statistical difference, or there is statistical association or relationship. Why? This is the rejection. This is what you call the bell-shaped type of uniform data. So, and you calculate and you come up with a p-value that is less than 0.05. Now, that means you have to reject, you must reject what we call the null hypothesis. When you reject the null hypothesis, it means you accept the alternative hypothesis. And we say that null hypothesis is no difference, no relationship, it's equal. Yeah, it's equal. Not, you don't say no equal, equality. No, it's equal. So no difference means that it's equal. No relationship means it's equal. There's no difference. So that's null hypothesis. So when you reject it, you will say there is a difference. So you will accept the what you call the alternative hypothesis. So, for example, I do this particular. Let me give an example of a research that I did. Cytomorphological abnormalities, or rather, the cervical abnormalities among diabetes mellitus patients. Yeah, and I checked their HbA1c. From the HbA1c, I look at these patients who have cervical abnormalities. And for example, I want now to find the relationship between cervical abnormalities and HbA1c. So I can come up with this. There is no relationship between HbA1c and, yeah, cervical abnormalities. Then I test that assumption. That is the hypothesis, an assumption. Now, when I test, I found that my p-value is above 0.05. Then that means, yes, there is something that has to be done. I will have to reject what we call I'll have to reject what you call the alternative hypothesis, and I will accept what you call the null hypothesis. So here I'm saying that now I'll say there is a difference, because of course I'm accepting the null hypothesis because my p-value is greater than 0.05. So I'll accept the null hypothesis, which says there is no difference, meaning that it doesn't matter your HbA1c or your sugar levels. All of those who have sugar levels that are either high or low, they have cervical abnormalities. So there is no relationship between controlled sugars and those who have not controlled sugars, giving, for example, a prediction on if they can have a cervical abnormality. Now, this area sometimes gets confusing, and I need just to repeat it. So for clarity, we have null hypothesis, which means it's a hypothesis of no difference, no relationship, or equal. And we have the alternative hypothesis, which is the one that says that there is a difference, there is a relationship, or it's not equal, not equal. So that means there is a difference, a relationship, or not equal. So let's take, or let's take, for example, hypothesis of there is no association between um, satisfaction of laboratory clients and the the number of visits, yeah, they have made, for example, in our laboratory. So you come and calculate using your software, which we'll share in a short while, and you find that your p-value is 0.02. That is below 0.05, which is the rejection region. So once, what we're saying about the rejection region, when you can see from this graph, anything below 0.05 as a p-value, it falls on rejection region. That means you will reject your null hypothesis, because in research you always don't write alternative hypothesis. You always write a null hypothesis. There is no difference. There is no relationship. There is the mean age of patients is equal. You know, there's no difference there. You mean that there's no difference. So when you're writing your research and you're giving that kind of assumption, then you find that your p-value falls within 0.05 less, 0.05 or less. Then that means now you will reject your null hypothesis and take up the alternative hypothesis, which will mean that there is a difference. And of course, if it is above 0.05, now you will not accept the alternative hypothesis. Rather, you will stick to your null hypothesis. Good. So another inferential component is the confidence interval. Maybe you've read papers and you've seen confidence interval, and somebody's writes this. So confidence interval is actually, it consists two numerical values defining a range of values that, with a specified degree of confidence, most likely it includes the parameter being measured. For example, you say confidence interval 76, and it's always written, as you can see, this red one, 76.3 semicolon 92.3. This means this is the population parameter. The correct parameter lies between 76.3 and 92.3, and we are 95% sure. So we have the confidence interval and the confidence level. So confidence level means I am 95, we assure 95%, or we estimate 95% that the true value of the mean of the population lies between 76.3 to 92.3. Now, that one you'll be inferring, you'll be giving an inference, you are giving a conclusion, you're giving a general conclusion, a general prediction where the true value lies, and you are 95% sure. Now, this is also calculated, and you come up with it in research, you give. So, you, for example, say 95% are sure that the population, for example, the mean age of this population that I sample lies between 76.3 to 92.3. Yeah. And we will see how this comes by. So now, for you to come with confidence interval, currently it's good when you have your software. You need to understand when you are able to do this, and for example, you're using SPSS, you're using R Studio, which I look forward in future to have a session whereby we can pull ourselves and do R Studio, using R Studio to analyze data, and it's very simple. But before that, you must have a background to understand how you are going to analyze this data. At what stage are you going to give descriptive statistics, followed by inferential statistics? Have you given a hypothesis of your data? Yeah. For example, you're comparing two machines. So you will say there is no difference in a full hemogram machine A and full hemogram machine B. There's no difference of results. For example, you're comparing two machines in your lab. So you'll say there's no difference. That's a null hypothesis. And now you come and do and calculate and get the p-value, come and get CI, the clean, I mean the confidence interval, come get your confidence level. And mostly people will use 95% confidence interval, confidence level. Now, this other portion is very important. When do you choose a statistical test? You may know software use, you can be using SPSS, you can be using RStudio, Python, and so forth. But when you make a mistake and use a wrong statistical test, for example, if you want to publish a paper, that paper will be rejected. Because if you use a wrong statistical test, then you'll give a wrong implication, you'll give a wrong conclusion, you'll give a wrong prediction. And it is important to know, and I'll just go through it simply, shortly. If you are comparing groups, you will ask yourself, first of all, you ask us, what type of question? Am I comparing groups between diabetes and maybe hypertension? So those are groups you'll be comparing. Or am I giving a prediction, an assumption? So if you're doing an assumption, you use a different test. If you're comparing groups, you just want to compare, for example, we have diabetes patients and hypertension patients. Let's talk about diabetes patients and maybe maternity patients, and you want to compare these two groups, their satisfaction. So you see, these are totally different groups. You're not giving any prediction. But if you want to predict, for example, is there a relationship between maternity and diabetes, diabetic clinic? You see, that's a relationship you want to predict. So if you're comparing groups, and the type of data is numerical, the data you're going to collect is numerical, you will ask yourself, how many groups? If it is one group versus known value, it's just a single group, and you want to find out about a known value, you will do what you call a t-test, which sometimes is referred to as Wilcoxon. So if you're getting even on SPSS, you'll do a t-test because it's one group versus some known value. If there are two groups, you will need to bring us to understanding. Is it independent or paired? By independent, I mean, for example, you're looking at control, and maybe you're looking at maybe treatment and control. Those are independent. They do not relate, treatment and control. But if it is paired, it means you are looking at before and after. For example, somebody is given antihypertensives. You took their BPs, that is before, and you gave them hypertensives. Hypertensives, and you took, and this, for example, maybe this is a good research that somebody can venture into. You want to get HbA1c on a patient who has not taken a certain drug, and maybe they take the drug, and you measure HbA1c after 2 hours of taking the drug. So you see, So this patient is paired because they have something before and something. So it is related. But independent, there are two groups that are not related. So you'll have what you call the independent t-test. If you're doing a software check, you use the independent t-test or Mann-Whitney test. If it is paired, you'll use what we call paired t-test, which is also called Wilcoxon. Yeah. So if you use that paired t-test, you will now give the correct results. Now, if there are three groups, and this, remember, it is numerical data, and you are comparing groups. Now you use what you call ANOVA, analysis of variance. Yeah. If you are now checking on prediction, you are looking at the prediction. First, you're taking on relationship, and you will either do correlation, which is Pearson, or you'll do prediction using the linear regression or logistic regression, or you'll do, if a linear regression actually is used when it is continuous outcome, meaning that your data is continuous. It means that your data can take even decimal points. So you'll use linear regression. For example, RBS 5.7, 5.2. But if it is a categorical outcome, one that is not continuous, it's just a category, you'll use what you call logistic regression. So you pick on logistic regression. Okay, so the other way to take it, if you want to do what you call a parametric test, which I'll just share in a short while, it's the parametric test. You look at, is the outcome categorical or quantitative? Because the predictor variable is the first that comes in. Now, is the predictor variable categorical? By meaning categorical, for example, you're saying type of disease. That's categorical. Quantitative, you're talking of maybe age. Yeah. And so when you do this, you will decide if it is categorical, the predictor variable, which is the independent variable that predicts the other. The outcome variable, I said, is the dependent variable. If the outcome you're going to measure is disease, the type of disease, then that is categorical. If it's quantitative, that is a number or numerical. Now, if that categorical predictor and you have an outcome that is quantitative, then now you'll choose either an unparametric test. But if that is it, you will continue up to ANOVA or MANOVA as expressed here. But if it is quantitative predictor, for example, you want to say RBS predicts. Maybe you want to say RBS. If somebody has high RBS, they might have a higher HbA1c. So you see, the predictor variable is RBS, which is independent. And for example, your HbA1c is now is your outcome is the dependent variable. And it's quantitative predictor, quantitative outcome. You will go and use what you call multiple regression. Yeah. But if it is only one variable that you want to measure, you'll use simple regression. But multiple one will be used if there are many predictors. I mean, many variables that you want to measure. Yeah, within the outcome. I mean, the predictor variables, there are many, and you want to measure one outcome. So, for example, you want to use age to predict HbA1c. That those who are elderly, maybe they can have a high HbA1c, and you want to use also RBS to predict HbA1c. So you will use multiple regression because you're using multiple variables here. So you're going to use what you call multiple regression. So basically, before you do any data analysis, you have what you call the statistical test assumptions, and you want to talk of independence of observations. That is, they're independent. The observations do not relate. They're independent. Homogeneity of variance. We talked about the variance. If the variance of each group, two groups, the variance is the same, so it is homogeneous. Normality of data, we talked about the distribution. Is it bell-shaped? So if it is normally distributed data, then that's okay. But if any of this is defied, these are called assumption of statistics. The observations are not independent, they're dependent. You will now change. You will not use parametric. You'll use what you call the non-parametric statistical tests. And these are examples of parametric tests. One is regression, another one is comparison test, another one is correlation. What about regression? Is a cause and effect relationship. You want to see what is the cause and the effect. And once you want to calculate a regression, you want to look what is the cause of that outcome. So that becomes regression. Comparison, you want to see the differences among groups. So that's a test of comparison. And correlation, you want just to check how they are related without hypothesizing the cause and effect. So here, in correlation, you're not interested on which is the cause and what is the effect. No, you're just like, how are you related? Are you negatively related, positive correlation, negative correlation, or there is no correlation? So in regression tests, it can either be simple, which you mentioned, it can be the multiple linear, and these just are examples that we can look at. For example, simple linear regression, you're looking at a continuous predictor variable, and the outcome is also continuous. So you're looking at RBS predicting, for example, HbA1c. So you will say, what is the effect of RBS on HbA1c? So you start measuring and see this one has a very high HbA1c and they have a higher RBS, or this one have a low RBS and they still have a high HbA1c. And now you come up with a simple linear regression and say RBS is related to HbA1c or not related completely. So multiple linear regression. So you might have two or more predictors, which we just mentioned. And for example, they are continuous, meaning quantitative. So what is the effect, for example, of income and minutes of exercise per day on longevity? So you come up and you want to get longevity as your outcome variable. Income and minutes of exercise per day now becomes your multiple linear, your predictors. And now here you use multiple linear regression. You don't use simple linear regression. Otherwise, you'll get wrong results. Now, logistic regression, I have age, but I want to understand about male and female binary. So that's when you talk of binary, we're talking about categorical. So it's a category. So it's a categorical one. So, for example, what is the effect of drug dosage on the survival of a test subject? Yeah. So drug dosage can be given as continuous 2.0, 5.0 milligrams, 5 mg. But now, what is the survival of a test subject? So that becomes, will you survive or not survive? Now, you see, this is bringing in a continuous variable and a categorical variable. And so here we have what we call logistic regression. We don't use simple linear regression and logistic regression. And this is key because when you be writing your paper, you will say logistic regression was used to determine the relationship. So association were tested using logistic regression, or association or relationship was tested using simple linear regression. But if you tell people you use logistic regression and it was continuous predictor, continuous outcome, then that means your research is not correct. This is an example of regression line. You see, you come up with a regression line, and even you can put it in your thesis, you can put it in your research, and you can see now this means that there is a certain y is equals to -6, 1. So there is this equation that can predict. It means that if you are at 80 abdominal, deep abdominal EAT, then there is where your waist can be confirmed. So using that deep abdominal area in centimeters, you can now predict the waist circumference of somebody. So you see now you are at 100, you can be able to use the equation and confirm that this can be a waist circumference of this. Now that becomes regression. It is a cost effect. But when it comes to comparison tests, they're like pair t-test, which we did independent. We spoke about independent t-test. I mentioned about this, and so maybe we may not go through them again. But we talk of ANOVA when there are more categorical variables, one or more predictor. And so we have quantitative variable here, so one outcome. Now, what about correlation? I'll speak about correlation. In correlation, we say you are looking at the relationship without minding the prediction. You're not worried about what is the cost effect relationship. What you just know is salary related to, for example, talk of a salary related to maybe you want to measure satisfaction or something. But here we will be talking about continuous variables. Huh? So continuous variables, like two continuous variables, for example, you want to see is okay. Let's take RBS and HbA1c. Is HbA1c correlated to RBS, random blood sugar? So you see the first on the left, these particular Pearson's R. You use Pearson's R. This particular graph A, you will say that it is positively related because it's going on the positive side. You don't care what is the cause or what is the effect of the relationship, but you just understand that now this tells you HbA1c and RBS are what you call positively correlated. Then these are negative correlation. Then when it appears like this, there is no relationship. It is just a scatter. There's no relationship in that case. Now, in non-parametric tests, you don't make assumptions because assumptions have been overridden. there's no homogeneity, there's no independence, and there is no normal. The data is not normal. So you lose what you call non-parametric test. And I'll just mention about them. They are like chi-square. When you're using chi-square, you to give out information about your data, it means that your data was not normally distributed. So you can use a chi-square test. For example, if it's a categorical versus categorical. So you want to look at, for example, talk of cancer, cervical cancer, and diabetes mellitus. So these are categories. Do you have diabetes? Yes or no? Do you have cancer? Yes or no? So you see that one, you use a chi-square because they are categorical. They are categories. And you're not going to do here regression, of course, because they are categories and you want to just get to understand the association. And so in this case, now you will come up with what we call the chi-square. And there are many others like Kruskal-Wallis, and which will not handle, but chi-square is the commonest one. Kruskal-Wallis is commonest. Also, Wilcoxon rank is another one which you can use. Now, while doing data analysis, you will pick finally either to use SPSS, you can use Tableau, you can use Power BI, you can use Invo, you can use Python, you can use R Studio. The commonest one currently is R Studio because that is the highest, because it's more of you use what you call commands. And that is the best because it gives you very good data analysis preview, and gives you very good data analysis, even including graphs. But you cannot use you cannot use these softwares without understanding the type of data you are analyzing and the correct statistical measurement that you need to provide, so that you can be able to come up with the very concrete information to speak about your data. And that's the end. Actually, biostatistics is the business of life hidden in numbers, engrossed in research. So if you want to do research, which I advocate for within the laboratory framework and laboratory personnel, there is one very key thing that we need to get, that we need to have a basics in data analysis, so that you can use your data to communicate in conferences, to communicate in publications, write papers, and communicate your data by giving valid conclusions, valid inferences, valid descriptive statistics. You must understand what it entails and what is the data you are having, how can you classify that data, what kind of variable you are holding in your hands, which variable are you interested in measuring, which particular test you'll put in place to ensure that your data is correctly defined. And back to you. If there is any question, I'll be ready to answer.
Thank you very much, Seth, for that insightful presentation. And I think this was quite timely. And I think those of you who have tuned in will agree with me that this was quite great knowledge that all of us need for our progression. So I am also sure that maybe a few were lost somewhere, but don't worry. Don't worry. If at all maybe there are places that you did not understand, this is not done overnight. But we will arrange more trainings so that you can be able to familiarize yourself with this terrain. So I can also read your presentation, your comments. Those of us who have been able to tune in. But just from the onset, thank you, Seth. This was quite wonderful and quite timely. So I'm going to allow time for questions and, of course, answers. And also, I'm going to allow for comments, those of us who want to comment. So be free to write your question or to just jot in your comment in the Q&A section. But also, if you want to speak, I'm going to give you the right to speak. Dr. Helen, I've read your comment, and maybe I'm going to give you the first chance to just comment. And Dr. Helen is our CMLC coordinator for Kisumu, and also the CMLC chairperson the CMLC Caucus chairperson. So Dr. Helen, I'm going to give you a minute. I've read your comment. You can maybe give general remarks, especially as the laboratory fraternity grows, because this is growth indeed. So Dr. Helen, if you can hear me, you can just unmute and proceed.
Thank you so much, Fred. Seth, congratulations. I'm so impressed, and I really enjoyed the presentation as one of you. And again, in another world, I'm a supervisor of many students that come with their research work. But what I've come to realize is that 80% of the students do not even understand why they are conducting their research. And the part that is really making them to fail, even in a simple presentation, is these topics that you have handled. They are mixing the qualitative, the quantitative. They do not understand it best. Thank you so much. I'm glad. And I want to believe that students in the platform have appreciated your presentation. And together as a team, maybe they can consult, they can look for you in the sideways so that you mentor most of them. That's it as a supervisor. As an MLO, honestly, we have grown and we thank God for this growth. Let us hold each other's hands. And I want to believe at Wamalwa Kijana, you have colleagues that you can mentor small by small by starting just to analyze that data. And I really liked your presentation because both of the examples that you are giving were lab-oriented. You are giving examples on sugars, you are giving examples on, name it, the lab tests that we are conducting always. It means the data that you are having in the lab, right from the lab request forms, through those our primary registers to the summary registers, can speak to the whole world, actually make us to do a policy that is binding, because it will be a policy that is made out of research, out of data. It is not just a policy that we see, wake up in the morning and feel that today we want to change this policy without any reason. So for me, I'm glad, and thank you, LMSK, for choosing right, because this is a topic at the right time, and it is also an eye-opener to most of us in the room, and we appreciate that so much. Asante sana, and God bless.
Thank you very much, Dr. Helen, for finding time, and also for the very, very wonderful remarks. We want to thank you also for, encouraging us. There are those of you who have already progressed to masters, to PhDs, and we want to say that you've opened the path for many of us, and thank you once again for the very wonderful words that you have shared. So team, at this time, I'm going to ask anyone who wants to comment. You can just raise your hand. I'll give you the mic. You'll be free to comment. But meanwhile, maybe I can read a few of your comments here. And this is Janet Juma says, clear and understandable. James Njuguna, thank you. Well articulated. And this is Abel Nduki, wonderful presentation, Dr. said. Lilian Arita, very valuable information. Moses Kakoi, let us join hand to LMSK Academy Powerful. Thank you, Moses. Steve Kimachu, that was a great presentation. And Henry Omondi saying is a statistician. Okay, thank you. Bahati Orembe, great presentation. Dorcas Chelangat, nice presentation. Daniel Tomno, excellent presentation. Fatma Sumba, good presentation on confidence level. And then Moses Ogoe, okay, thank you, Moses. I think there's one question from Collins Oyangi, and maybe I'll read it. We are required to have data protection certificates. What is it and how is it obtained? I'm sure we shall help you. And then, yes, so maybe we can start that from there, Seth.
Yeah, thank you so much. As we
Seth, we
generate a
lost you.
lot of data, and you can see HRIOs presenting those data in different places. You can see many people, even during the COVID-19, you could see every person stand with the COVID data and say, this is the data. It's from the lab. But the lab itself could not analyze the data and say, well, this is what it means. This is what we have in place in this place. So I invite us back to that. And now to answer the question that has been presented on data protection certification, there are those mandatory to be certified mandatory, and that includes the actually the like the the HRMs, the human resource officers. They must have the ODPs because they are coming data protection officers. They are those mandatory, but there are those individual that you can take it on upon yourself, and this can be found within the Kenya School of Law. You can Strathmore also has some, and I'm looking forward to those that will even provide online, so that we are able to get trained on data protection, because we have the Data Protection Act. And of course, once you've gone through the research ethics, that is also another form of getting it right when it comes to Data Protection Act. So ensure that when you're doing that, any research you want to publish, for example, even within your hospital, ensure that the hospital management is notified about it. If you have a county ethics board, let it be notified. And you can obtain this even from other institutions like KMTC, Maseno University, and the different ones. So, but for Data Protection Act training, the most common one, you can get it from the Kenya School of Law. You can also get it from the Strathmore, yeah, and many others places. Yeah, thank you. Back to you.
Thank you, Seth. I want to confirm if there's anyone who has a comment or who wants to speak. I'm going to give you this chance to make your comment. And Dr. Caleb, I can see you in the house, and we celebrate these our colleagues, and I'm sure they may not miss something to say. Dr. Caleb, I can see you. If you can unmute, you can also make a comment. Dr. Caleb Onyango, you're in a position. Okay. Dr. Caleb, you can just unmute and proceed to make your comments. Or any other person who feels that he wants to say something, especially around this area, you are free to just raise your hand. I'll be able to see, and I'll give you the chance to make your comments. Yes, Dr. Caleb, proceed. You are muted again. Just unmute and proceed.
Hello.
Yes,
Hello.
proceed. Yes, we can hear you.
You can get it now.
Yes.
Thank you so much. I'm very grateful to our presenter. He has really handled a very voluminous area that many of us sometimes a lot of challenge, and he has tackled all corners, all aspects of the study that anyone intending to do a study would wish to learn. It's a wonderful presentation. I'll only encourage our participants to keep in touch with the ongoing presentation. There is still more to be learned. There is still a lot to be learned on this aspect of research study. Maybe just one area that he may need to clarify to the participants, the issue of confounders. How does it affect the study results, and how do we control confounders in a research study? How does it affect the study, the conduct of the study, and how do we control? Just for the benefit of many of us. Thank you.
Thank you so much. We celebrate Dr. Caleb. He's one of us, and he also has a PhD in cytology. I'm sure it's cytology. Thank you so much, Doc, for that. Back to you, Seth, if you have something.
Hello, Fred. Thank you so much. That is a very good question. Confounders are bound to be there in research. And one way to deal with confounders, number one, you can decide that, for example, you're doing a study. Let me just use a very simple example like diabetes. You want to study diabetes in relation to a certain condition. And you get people coming with diabetes and others have diabetes and hypertension. So hypertension becomes your confounder because it might interfere. So there is one way you can decide to ensure that all people you will sample, they are only diabetes and they do not have hypertension or other underlying conditions. So you will ask, do you have any other underlying condition? Then these people are exempted. So that one we will call criteria, that is the exclusion and inclusion criteria. So using the exclusion and inclusion criteria, you are able to manage the confounders. Another way, if you can't really do that, because most people who have diabetes probably they still have, and confounders can distort your results. They can put your results under stress. You can have your results revoked. Now you will need again now to understand how to control them. And during controlling them, you'll do what you call randomization. You can use randomization. That is randomly assigning participants to groups, ensuring that both known and unknown confounders are distributed evenly. So those who have diabetes alone, those who do not have diabetes, now it's a random. Or you can come what you call matching. Matching is commonly used in research, and this you select a comparison group that matches the treatment group. So this means you can do this, those who have diabetes alone and those who have diabetes and hypertension. So you are matching, and you are able now to come up and say, well, this hypertension for sure is a confounding factor for that particular result that you intended to get. Yeah, and there are many more others, but those are the commonest that I can mention as it is for now. But again, when during analysis, you can do what we call multivariate regression, where you do multi, those who had diabetes and hypertension, those who were aged with hypertension, diabetes, those who are young. So you're doing a multivariate, and now you come up with data from that. That is a bit huge, which I cannot speak right now. But in future, when we'll be now doing a practical analysis, which you can project online, then we can be able to do that. Thank you. Back to you.
Thank you, Dr. Caleb, and also for that eye opener, and thank you, Seth, for the wonderful response. So, Tim, I want to bring another question here from Moses. He's asking, when writing a research, must it include a hypothesis? Okay, thank you, Moses, for the question.
Thank you, Moses, for that question. Now, you will be the one to decide your research. For once, for example, you want to do what you call prediction. If you're doing a research within prediction, you want to predict something, you must write a hypothesis. But in the event that you're doing a comparison study, you want to just compare, but you don't want any prediction, then you may not need a hypothesis. However, at this level, beyond MSc, you require to MSc, you require to have a hypothesis in your research. So I was giving it an example of you're comparing, for example, the mean survival days, maybe not really survival days, that's not a good one, but the mean, maybe talk of something about the mean. Let me just use mean of female patients and the mean. You are comparing the mean of male patients who come to the lab. Are they the same? Or maybe you are having very many males who are old and very young females. So there could be something different there that you want to communicate. So you will compare that. But of course, if you want to say the prediction that there is no relationship between the mean age of those gender, I mean, of female gender and the male gender who are coming for the services within your facility, then that also means something. So it's a prediction, and that means you need to have a hypothesis. And the key thing about a hypothesis is always you write your hypothesis in a null statement. Null statement means there is no difference. There is no association. It is equal. Then when you test it and it gives you something different, when we said about the p-value now that's when you make your total prediction that now the assumption held was correct, or the assumption held was on the inverse. It's not incorrect. It was on the other side. Now you make your comment on that. But I would encourage us that we learn to use hypothesis, because that is the key. Because in most cases, even in clinical trials, they will do a hypothesis that drug A has no difference with drug B. They don't say that drug B is better than drug A that is existing. You will say drug A has no difference with drug B. Then now when you'll get the difference, now you'll say there is a difference, either on the positive side or on the negative side. Yeah, and back to you, Fred. Thank you.
Thank you. Wonderful. That's wonderful said. So I think, team, we have come to the tail end of today's session. And indeed, Sad said earlier that don't be worried if at all there's something you did not understand very well. We shall try as much as we can to bring a series of these presentations, including a practical guide that we'll be able to project on the screen, and maybe you will be able to relate well when that is done. So just keep checking on our presentations, and you will see how it relates to your day-to-day practice. Otherwise, I want to say thank you, Seth, for the wonderful work. And I also want to say thank you for those of us who are asking for the contact from Seth. I think it has been shared on the chat box. You can always reach out, for further clarifications or mentorship, as had been alluded by Dr. Helen. Otherwise, team, we have come to the end of today's session. And until next time, I want to give this chance to the speaker for his closing remarks.
Yeah, thank you so much, Fred. And back to the entire MLS, I really suggest to you very strongly that let's venture into data analysis. Let's venture into research. That is how we can grow our profession. That is how we can reduce our numbers within very little resources, scarce resources. We cannot keep on fighting within the lab. There is only one way. We must go outside the skirts of the lab and show our potential. Otherwise, all of us cannot be CMLCs. All of us cannot be within the jurisdiction of the CMLCs, lab managers. The only way we can get into academia is through research. And a very good plea to you again is that we have data. So the greatest team of healthcare workers who should publish papers compared to any other group, it is the lab, not any other person. But is that true? We are not publishing papers. Many other colleagues and friends from other different professions, they are coming to us to take data and publish using our data. But this is my plea to you. Let's use our data to build ourselves. It is possible, and it's very, very possible. And back to you. Thank you. Until next time. Thank you, Fred.
Thank you, everyone. And on behalf of LMSK, we want to say